Hello, everybody. Welcome to this new live broadcast. I am very happy to be here today for this third live mission design where we're starting the first part of the spacecraft sizing. It is going to be I am very sure those who are online now may or may not have been in the first two. Maybe they were, maybe not. If you were in the first two, welcome back. If you were not, welcome. It is possible that you missed the first two. If you did, then it's available. It's available on the different platforms. We're streaming directly to YouTube and LinkedIn. So on any of those, you'll find the history. Right. Today, let's start off by recalling what we did. We already mentioned the purpose of this space mission, right? I'll refer you to the very first video. We took some time there. And then we did a little bit of the sizing of the mission. We went through what the whole mission is about, what are we trying to do. Now, we're going to start with the sizing of the satellite supposed to accomplish this mission. Open here is the directory that you know about. If you have been here before, then you know about this directory. Why? Because I shared this directory with you. Every NMD association member is welcome to log in and check their member portal. I'm going to make these files available. We're trying to make it possible with the dev team. Succeeded. So I'm uploading these mission files and the satellite files so that you can access them directly from your member portal. This is so that every NMD association member can access all the files we're building together here live and use them as templates, use them to build their own, have fun with them. So this is the IDM file. As I mentioned, we're using IDM CIC, Simu CIC. We're using the tools from the French Space Agency. And interestingly enough, I did something really cool. Those who follow me on various social media platforms know that I use custom, I'm a fan of custom AI, offline AI, LLMs, right? RAGs, as they call them, retrieval augmented generators. So what I did is I took one and I did a very specific RAG. I'll tell you about it just now. So looking at the mission as we discussed, we mentioned that we would like this satellite to be able to communicate with the entire TinyGS community, all the TinyGS ground stations all over the world. There are not so many in Africa, there are more and more, but there's a big community, and it would be fantastic that this space mission be TinyGS compatible. Now, that is a fantastic shortcut. It is not, it's for the purposes of facilitating wide-scale learning that we made this choice. And it is a fantastic shortcut because the best Pico satellite model to copy for TinyJS compatibility is FossaSat 1. And FossaSat 1, I was fortunate enough to talk with Julian not too long ago. Let's just make sure this connection doesn't go away. Yeah, I was fortunate enough to discuss with Julian not too long ago about this, and at the time he said to me, well, go to the Fossa GitHub and use all the models. They put the whole thing there. It was a while back, and so I figured, okay, now is a good time to take him up on that offer. And it's like a template. Everybody, quote unquote, who's building a Pico satellite would have probably consulted this GitHub repository. So I went there and I took not really FossaSat 1, but FossaSat 1 and FossaSat 1B, because there are some modifications that are done on 1B. And basically, if we can build something that follows the FossaSat 1B design as hardware and software, as it exists in the Fossa repository, GitHub repository, we de-risk the satellite significantly, right? So this is what I did. And everyone who is part of this mission and interested in getting their hands dirty in building, there's a repository. I'll share the URL as part of the files that are, but it's really easy to find, as part of the files that are going to be available. So what I did is that in this LLM that is in the form of RAG, I loaded every file available. So I basically downloaded the FossaSat 1 and FossaSat 1B repos from their GitHub, and I loaded it in my local LLM on my computer. Then I loaded the documentation from IDM CIC and CMU CIC and a couple of other IDM tools like RFComLink and so on and so forth, and loaded them in the LLM. So I was sitting with this local offline LLM that now understood much about FossaSat 1, FossaSat 1B, IDM CIC, and so on. And then we had a bit of a chat, right? And very interesting, I could then quickly do some analysis and extract what was the mass budget, what was the power budget, how did they think about the link budget and things like this. So I extracted that. I'll share that with you just now. Just for kicks, I went back and looked at what it would be like on the Gemini. Strangely enough, it was just about the same thing, right? Because I thought, okay, let's see what you get on something that is a public LLM. And of course, you get some differences, but because I know what the story is about, essentially in the content, it's the same. And it's very interesting that you can do this, okay? If you want, you let me know if you want me to show you a little bit how I got to set up the local LLM to be able to understand these things, and then you can now chat with your chatbot offline if you want. Right. So today we're talking, and welcome if you're joining us just now. Welcome. Take a seat, grab something to drink. If you are joining us just now, we're doing the spacecraft sizing, dimensioning, whichever word you want to use, for our mission 237. And we're going to use the FOSSASat 1B in particular as a template. Why? Because that is the safest, lowest risk pocket cube that is TinyGS compatible, and its design is openly available, and we're going to go with that. So, what is spacecraft sizing, dimensioning? There is a very simple way to think about it. Essentially, you are answering a few basic questions. How heavy will the satellite be? How much power will the satellite consume? And will you be able to communicate with the satellite successfully for the duration of the mission? For a satellite like this, it's if you answer these questions, you got it. That's about it. There is another one that has to do with the data budget, which means, okay, how much of the mission data will I get for each pass? But you only have a problem with getting data if you can communicate with the satellite. So the key question is, can I have a link? Can I talk to the satellite? Can the satellite talk to me? How much power will this satellite consume? How heavy will it be? The mass has to do with how much it will cost to launch and what opportunity you have to launch. What are the launch constraints? So you're worried about the mass because the cost of launch is per unit mass. So the heavier the satellite, the more expensive it is to send it to space. You're concerned with power because you need to know that there is enough power to do, the satellite has enough power to do what it's supposed to do. Because if you run out of power, that's the end of your mission. And you want to make sure you can talk to the satellite and the satellite can talk to you, because otherwise you don't have a mission. Okay, let me show you what got out of my conversation with LLMs, having given them some context about FOSSASats and the tools we're going to be using, IDM-CIC in particular, because this is what we're using for the satellite. All right. I am first going to share with you the summary I got. It's important. So this comes out of the documentation available on the internet on FOSSASat. Is an upgrade on FOSSASat 1. Okay, beautiful. So, what are mission modes? I'm going to describe to you this table. I will attempt to make it very, very simple. Mission modes here, what I asked when I was prompting my local offline LLM was, okay, now you have some context with FOSSASats, you have some context with the tools. Now, we're going to be using IDM-CIC. IDM-CIC has a logic on how it thinks about modes. So how would you break down the mission modes? Essentially, what is the satellite doing? Think about it as what is the satellite doing? What is the set of things that the satellite can be doing? A full list. If the satellite is not doing this, then it's doing that, and so on and so forth. And basically, the satellite can be in startup mode, which is as soon as it is ejected from the pod or the rocket that launched it to space, that's what it's doing. It's in startup mode. When it's done being in startup mode, it's going to be in deployment mode. And then it's detumbling, or detumbling, then deployment. Generally, is one or the other. You typically a hold of the attitude of the satellite before you deploy antennas and panels. So I would go with detumbling first and then deployment. Then it has its nominal mode. Nominal is normal. So what is its default mode, so to speak? And when it is busy doing its mission, it's active. I would call this something else. But when it's active, and it could be on safe mode for one reason or the other. Something happened, then it goes on safe mode. So if we have some sort of a list of things that the satellite is doing in orbit, this is a list we can use. It's a good starting point. Maybe we iterate as we dive deeper in the design, but this is a good place to start. How long, more or less, can the satellite be in one of these modes? This is the duration. And while in each mode, what is the onboard computer doing? What is the communications subsystem doing? What are the power losses? What's the deployer doing? And how much power is it using, and so on and so forth. So this is a simple table that says what's the satellite doing. And as it is doing what it is doing, each of its subsystems does what. So startup mode corresponds to how much power used by the OBC, how much power used by the comms, and so on and so forth. And this, like I said, these I prompted to sort of summarize the existing documents on the basis of how it would best fit the IDM ecosystem, right? Why? Because I'm going to use the IDM ecosystem. And today is just the first part of sizing, and I'm trying to get you to get a sense of what sizing is about. How heavy is this satellite? How much power does it consume? This first table has much to do with how much power the satellite consumes. So basically, when we will get to scenarios and we'll be simulating worst case scenarios, you'll see that it's important to see how much power is consumed for how long, and check the battery depth of discharge. Like, how is the battery discharging versus how fast does it recharge from solar panels, just to make sure we don't get into a situation where the battery completely discharges before it gets a chance to recharge, because then you would have killed your mission. The mass budget, again, this is on the basis of what is existing in the FOSSA documentation and the IDM ecosystem, because the way IDM CIC works, it has margins. And I just wanted to see what would be the correspondence that would be proposed, to take a look and see if it makes sense. It does make sense. We're going to dive into it and propose a first version of the IDM file populated with these subsystems. You have the structure, APS, OBC, comms. I decided to add harnessing. It's not exactly an active one, just like one would argue, why don't you put it as part of the structure? I could, or not really. This is some people detach it, some. It depends on your philosophy of the how you think of your satellite. So I had to share this with you. So this is the beginning of the mission sizing. We are using the existing, and the existing that we choose to use is the FOSSA Sat1B. Why? because we want our mission to be compatible with the TinyGS ecosystem. Why do we want this compatibility? Because we want the entire TinyGS to participate in this mission. We are going to be transmitting data from sensors on the ground. This data will be sent over to, we'll look at the data budget and see how much data we'll be dealing with at a time. Will be sent over to the satellite, and this data will then be broadcasted to all TinyGS ground stations available in this will be this six lines active mode here. And essentially, as the NMD association, we will then share all the information with the community that will make it possible for them to decode this data and actually interpret it in terms of sensor values. And it will be part of this centralized database where everybody can see what the data is saying. This is particularly interesting because one of the things we want to be, one of the use cases we want to put out there, open via this mission, is sort of early warning, disaster management type of applications. So if we put sensors somewhere and it is transmitting data, if we are trying to achieve some early warning on some critical areas, we'll just map it and share, so that if somebody picks up a signal that is of concern, they can also share. The entire community can contribute to save lives like this. Yes, it seems a bit vague now, but as we evolve, will narrow down the specifications and it will start making more and more sense. But in a general overview, this is really what we're trying to achieve. Of course, the non-stop value added is learning. As we build one satellite after the other, people get to learn how to build. As we design, people learn how to design. As we operate, people learn how to operate. And this will be one where it will be possible to have practical experience in operating a mission. This is the reason why we are running this Missions 237 constellation. Next, what will happen is those who are in the NMD members who will have access to this IDM file will start populating this. Like I said, I could do it myself, but I'm not going to do it because I really want the members of the community to do it. And it has to be there are those who already have done the training. I can think of a few people right now off the top of my head. Who will, all these subsystems that are here, all these subsystems right here, there you go, are going to be entered here. One subsystem after the other. I think I can zoom in here a little bit so you see well. Here, so this, you will be defining new subsystems, add them, add some elements. If you want to know how this works, again, just join the association. The training on how this works is there, available for free. We'll fill this in and then make sure we'll check that the way we approach the design using IDM CIC, we'll see how far it departs from this design. And who knows, maybe I will reach out to Julian again at some point a bit further in the design, so that we take a look and maybe the guys from FOSA can comment on it. Maybe we invite somebody for one of these lives to join the live, and then we can have a chat about the spacecraft design, dive into the mission design, maybe replicate some part of the previous missions. Maybe we replicate some some orbital propagation of way back then when FOSSASat-1 was launched, and then see, run some tests together. All right, so this is the first part. It's only the beginning. The important part here was for you to understand what are we talking about when we talk about mission sizing. Not mission, spacecraft sizing, dimensioning. We have to understand how heavy will the satellite be. We have to understand how much power the satellite will consume according to what it is doing, because we have to make sure that however much power it's consuming, it doesn't run out of power. And we have to make sure we can talk to the satellite and the satellite can talk back to us. Essentially, this is it. I also had to share with you the fact that because we want TinyJS compatibility, the natural choice of a model to go by is the FOSSASat-1. But FOSSASat-1 was redesigned into FOSSASat-1B, which is a better version of it. And it's a really good starting point. It is very, very cheap to do. Of course, one will say cheap is relative, but honestly, it doesn't cost much. All right, that is the end of my story today. In the next part of the spacecraft sizing, we're going to dive into what the community would have done in IDM-CIC and push one step further. IDM-CIC, right, the way it is, we will extract from it the mass budget and the power budget right away. And we're going to open the other tools to look into power, more detailed, the power design and the link budget, and look at the data budget too. All right. Thank you very much for your attention. Thanks for sticking with me for the third time. See you again next week for the part 2 of the spacecraft sizing. Bye-bye.